Hello, I hope all of you are doing fine. Now, in today's session, we will briefly or in short, we'll try to understand what is projection, and as well we will understand how to get the projections of a point in the given quadrant system. Now, to begin with, let us first just try to understand what exactly is a projection. Now, projection in single word, if you want to define, it is image. Image of what? Image of objects. Now, these objects can be physically existing in a way, or they might be as under the process of creation, like in case of design. So I am thinking of something and I have the dimensions in my mind, and that way I want to give it a physical shape in a way on black and white. That is, I want to have the image of that object with the geometric details. Now, as this is engineering graphics, the dimensions of the objects or the drawing are very much important for us. So first let us try to understand how the logic of how we get an image. So we can apply the fundamental of kind of physics maybe. So let us say there is an object. Now this is placed in the space and I want to have its images. So for having the images, certainly I need two things. One, I definitely need a light source, right? As well as another thing which I need, that is a screen. So until and unless I have a screen, I won't be able to get the image, because the image I will be getting on some surface. So that will be the screen. So the light rays coming from the light source will strike the body, and I will be able to get the image of this object on this screen. Right now we are not bothered about that much the size. First we are trying to get the image. So I need definitely a screen and a light source, with the help of which I will get the image of that object. So I will be getting the image suddenly on the screen. Now the size of this image can be different than the size of the object. So if the light rays are scattered, definitely in that case I will get the size of the image to be larger than the object. Now, as I have said earlier, the dimensions of the object are of importance for us. That means I want the size of the image also to be of the size of the object. So for that, whatever these light rays which are scattered, I'll have to bring them closer, such that if this is say some length, say L, I should get the length in the image as well as L. So for that, so the light rays passing from this corner and light ray passing from this corner, they must come together such that they become parallel to each other. So these two light rays must get parallel to each other, as well as these light rays, they need to get perpendicular to the surface or the screen on which we are getting the image. Then only I get the same length or same dimension to be projected. Now I am using the word projected. So to be projected on the screen. So this is the first condition. So now instead of calling these now light rays, I'll replace the light source into an observer, and now instead of calling these light rays, I'll call these as sight rays. So I want the sight rays to be now parallel to each other and perpendicular to the plane on which, or the screen on which we are trying to get the image. So that means these rays, now we are projecting the image on this surface with the help of these light rays or sight rays. So these are called as the projectors. So, and we see that we will get this dimension to be as the same that of the object. So, the projectors are getting perpendicular to the screen on which we are getting the image. So, getting perpendicular means the projectors are orthogonal to the screen on which we are taking the image. Hence, these are called, or this method of projection is called as orthographic projections. So this method which we are following here is called as orthographic projection. So this is for sure now. To get the image of an object, so this is the object and the observer is standing at infinity, then only the sight rays will become parallel to each other. So the consideration is that as if the observer is at infinity. Now infinity means the distance of the object, as if distance of the observer from the object is quite large, or the dimensions of the object are quite negligible as compared to the distance of the observer from the object. So that we will be referring as infinity. Then only these light rays or the sight rays or the projectors will become parallel to each other and they will be perpendicular to the plane on which we are taking the image. Now here I have put the condition such that, so as if the observer is standing on ground, so I am getting the screen to be a vertical screen. Now in drawing we take this screen as an imaginary plane or imaginary reference plane which is vertical, so we are calling it as vertical plane, or in short VP. Now when we are taking the image, so in this case these light rays or sight rays or the projectors will pass through all the corners and I'll get the image of this object on the screen, right? But when I am standing here and looking at the object, I'll be only able to see this part of the object. So that means I am able to see this dimension, let us say I call this as L, length, and this as the height. So when I am looking at it from this side, I'll be able to see only these two dimensions on the image. So that means this one image or one view, I'll call, this one view is not giving me all the geometric details about the object. So that means then to see the other dimension, I'll have to turn the object. Now if I am turning the object, that means I am disturbing its orientation in the given condition. So instead of turning the object, we prefer to move the object. So now to see this, then I'll have to move up and look at the object in this direction. Then only I'll be able to say, if I call this dimension as width, I'll be able to see this dimension. Now here I don't have a screen, fair enough. So what we do, we again take one screen and put it horizontally. So what we did now, we put another screen which is now horizontal. So this plane is the horizontal plane on which we will be getting the image, and in short we will call this as the horizontal plane. So now when we look, so when these two planes are getting intersected, so at the intersection I get one intersection line. So we name this line as XY line. Now these two planes, the horizontal plane and the vertical plane, they are the reference planes. Hence we will call this intersection line as the reference line. So now when I am taking the image, so I move to the top and I look at it so that, or the sight rays will now come down. Again, following the condition of orthographic projection, the projectors will be parallel to each other. The projectors will be parallel to each other and they will be perpendicular to the plane on which we are getting the image. So in the top view, we will get the image of now this surface. So now we will be able to see this length as well as the width. So now these two views together, they are giving me complete geometric details of the object. So when I am standing in front and looking at the object, so I will be getting the front view of the object, and front view will be always on the vertical plane. So we will be getting the front view on the vertical plane, and this front view is also called as elevation. And the second view what we have taken, to get the second view, we move to the top. So this view will be called as the top view, and we will see that the top view will be always available on the horizontal plane, and the top view is also called as the plan. So these are the two views which can give me the complete geometric details about the object. Now there can be as well cases where even these two views are insufficient to give me all the geometric details of the object. In that case again, we depend on another view which is called as a profile view or the side view. That means instead of moving to the top, I can move, or the observer can move to the left and look at the object. So when I move to my left, then again I need to take a reference plane. So in that case, the reference plane will be somewhere here and the projectors will be perpendicular to, so I'll be getting the profile view. I'll be getting the profile view on the profile plane. So this is the side which I'll be able to see, and in that case I'll be able to see the width and the height in the image. Fine. Now usually in most of the cases all the geometric details are achieved in these two views, that is the front view and the top view. In case it is insufficient, then only we go for the profile view, and the condition of the profile plane is such that it is mutually perpendicular to both the reference planes. So it is perpendicular to the VP as well as perpendicular to the HP. So as if we are in a room, the wall in front of us will be the vertical plane, the floor is the horizontal plane, and the side walls are the profile planes. So when we are standing in the front and looking to the object, so we are getting the front view, and when we move to the top and look at it, so I'll be getting the image on the floor, so that is horizontal plane, that will be the top view. And if I move sideways, so when I move to my left, I'll be calling it as a left profile view or left hand side view, or when I move to the right, so similarly I can move to the right, so in that case the profile plane will be somewhere here, so I'll be getting the projection on this side of the plane. So that will be called as the right profile view. Now in this entire process, by considering those reference planes, what we did is actually we have divided the space in front of us. So I'm always referring me as the observer. So the space in front of the observer is getting divided into 4 zones, right? So this zone with reference to the observer. The first area or first volume is called as the first quadrant. The space behind the vertical plane and above the horizontal plane with reference to the observer is called as the second quadrant. The space behind the vertical plane and below the horizontal plane, it is called as the third quadrant. And the space in front of the vertical plane and below the horizontal plane is called as the fourth quadrant. So when we place the object in the first quadrant and take its images, we are calling it as first angle method of drawing. If we place the object in the second quadrant and take its images, we are calling it second angle method of drawing. Similarly, third angle method of drawing and fourth. And we always prefer to have or go for the first angle method of drawing and third angle method of drawing. That too, in present situation, we will be restricting our study only to the first quadrant. That means we will be applying only the first angle method of drawing in orthographic projections. So let us move our idea from projection of objects to projection of point. Now, why point is important? We can say the point is, so we will be talking about now projection of points. So in various conditions in the given quadrant system. So what are the restrictions we are doing here? First thing, that it is orthographic projections. That means the projectors are parallel to each other and they are perpendicular to the plane on which we are taking the image. And second, we are restricting our drawing to first angle of method of drawing. So that means the object is in the first quadrant. Fine. So now why we are trying to understand the projection of point. Now for any drawing, we will say that the smallest unit of a drawing will be a point, or the smallest drawing what you can draw is a point. So point is a dimensionless or an element with negligible dimensions, right? So if we are in a position to understand how to get the image of a point in the quadrant system, then definitely I can get the images of n number of points, and thus I can make my object or draw my object, image of the object. That is why understanding the projection of point is important. So let us consider the case, I'll call this as case, so maybe case 1, that there is a point P in the first quadrant which is H mm, so I am giving it a unit, say H millimeters above HP, the horizontal plane, and B millimeters in front of VP or the vertical plane. So that means absolutely this point is in the first quadrant. So let us try to first understand how the images is to be interpreted for orthographic projection. So first we will try to see the pictorial understanding. So this is the vertical plane, and so we are considering only the first quadrant. So this is the reference line XY, right? And there is this point P which is in the first quadrant. So there is this point P which is in the first quadrant. Now say, as if you as the viewer, the board is the vertical plane for you and the floor is the horizontal plane, and as if you are sitting in the first quadrant and looking at the point. So maybe say this is the point which is in the first quadrant, right? So how I can explain its coordinate in a way, so or its location in the quadrant. So this point P is in front of VP and it is above HP. So I have said that the point P is HMM above HP and B mm or B millimeter in front of VP. Now, for orthographic projection, what is the condition of the projectors? The projectors must be parallel to each other and the projectors must be perpendicular to the plane on which we are taking the image. And how many images we are depending on? We are depending on two images, that is the front view. So standing in front of the object or the point and looking at it, so this will give me the front view image, and then moving to the top and looking at it from the top to get the top view image of the point. Now my question will be, how many projectors can pass through a point in one direction? So it will be one. See, we can say that there can be n number of projectors can pass through point P, but in one direction only one projector can pass. And what is my consideration for orthographic projection? The projectors must be parallel to each other. Now there is only one point which is having negligible dimension. A projector will also have negligible thickness. That means for one view, only one projector will pass through one point in one direction, right? So when this sight ray or the projector, it will pass through point P, and wherever it will strike the vertical plane, wherever it will strike the vertical plane, there I'll get the front view image of the point P as P dash. So this is how we denote the front view with smaller case with the superfix dash. So P dash or P prime will be the front view image of the point. When we move to the top and look at it, again in one direction or the projector, I am taking the image which will be on HP. So this is the horizontal plane, this is the vertical plane. Here we are getting the front view, and here we will be getting the top view. So for top view again, the projectors must be parallel to each other, but there is only one projector because there is only one point and in one direction only, and I want that projector to be perpendicular to the horizontal plane. So the projector which is perpendicular to the horizontal plane passing through point P, wherever it will strike or hit or meet the horizontal plane, there I'll get the top view image of the point as P. Now we denote the top view with a smaller case only. So this is giving me the front view and this is giving me the top view. Now let us talk about the H and B millimeter dimensions which we have given. Now when you are looking at a point from the front, we will be able to see how far it is from horizontal plane, right? We will be able to see how far it is from horizontal plane. We will not be able to make judgment of its distance from the vertical plane. So if I am standing here, you cannot make out how far I am from the board, right? It is because we cannot see the dimension in the in the direction of the vision, right? Say like this, if I keep the pen this way, you are able to see this length or this dimension, right? But I keep the pen in this fashion, you won't be able to see what is the length of this line. Why? Because the length of this dimension length is getting parallel to your vision. So you are not able to see the dimension L in this case. So similar thing will be here. So when we are looking at it from the front, we are getting the front view on the vertical plane, but we will be able to see its height, that is the distance of the point from the horizontal plane. And this image, if it is parallel, if it is perpendicular to the vertical plane and the horizontal plane is perpendicular to the vertical plane, then this projector is definitely parallel to the horizontal plane, right? So that means I'll be able to see this distance h, right? And this distance, so I'll get the image at a distance h from the horizontal plane, or for that matter from the xy line. So I'll be able to see this h millimeter distance of the point P in the front view, and this distance, the minimum distance of the image from the horizontal plane. So this line which we are drawing or will be using to draw the images in the orthographic projection, this is called this is the projector of that point. So similarly, when we are looking at it from the top now, so when we are looking at this point from the top, I'll be able to see how far this point is from the vertical plane. I won't be able to see the height of this point. Now you must have experienced, if you are on the terrace of a building and you are looking at a person who is walking, you won't be able to make the judgment of his height, right? So similarly, so when I am looking at it from the top, I won't be able to see the height of this point, rather I will be able to see its distance from the vertical plane. And as we have mentioned here, the distance of this point from the vertical plane is b millimeters. So from the top, I will be able to see the b millimeter distance from the vertical plane. So again, this projector is perpendicular to the HP, that means it is parallel to the vertical plane. So saying this parallel distance is going to drop down. So I will be able to see that in the top view image to be b millimeters from the XY line, where this projector will be perpendicular to the reference line XY. Now this is a three-dimensional approach, pictorial representation to understand how we are getting the image. Now I have to convert this drawing into a two-dimensional drawing, or which we are calling it to be as orthographic projection. So orthographic projection for this condition, so for that I'll have to bring it to coplanar, right? So for that, what I need to do, so what I'll do is, or what we do is, as if we rotate the horizontal plane by 90 degrees and make it coplanar with the vertical plane. So when we turn the horizontal plane, so obviously the top view image will also turn with it. So as if this dimension will rotate about the XY line, and so this is that projector which remains perpendicular to the reference line or the XY line, and the top view image comes to this position. So now the vertical plane and the horizontal plane, so this is the vertical plane, this is the horizontal plane. What we did, we have rotated the horizontal plane, and we made both these planes coplanar. So now if I turn it this way, I can represent the positioning of this point with the help of orthographic projection. So first we will be always drawing the reference line xy. So this is the reference line xy. For one point there will be always one projector, and the condition of the projector is that it will be always perpendicular to the reference line. So I can draw the projector for point P. So as if I know what is H, so H is getting represented from the XY line. So I can take this distance in my compass or scale and I can mark that distance H. So wherever at H distance, I will be getting the front view image of this point as P dash. And similarly, if I know what is B, I can take that distance, I can measure that distance, and that B distance is also from the XY line. So from the XY reference line, I mark, measure the B millimeter distance, and I get the top view image of this point as P. So in the front view, we are able to see this height to be HMM and this distance to be B millimeters. So that is how we get the projection, orthographic projection of a point in the first quadrant. Now let us talk about another view. I'll show it to you again. Let us understand first what is the side view or the profile view. Now as far as first angle is concerned, we will be always going for the left hand profile view until and unless it is mentioned. It is a kind of an unwritten rule. So usually if we are going for the profile view, we prefer to go for the left hand side view, right? So for left hand side view, that means as an observer, if I am standing here, this is the front, this is the top. So I need to move to my left, right, to get the left hand side view. So as an observer, then I will be standing here and looking at the object in this direction. So this is my left, I move to my left and look at the object. So in that case, the profile plane will be at the other side. So this will be the profile plane or the left profile plane, sorry, the right profile plane, but the view is left hand side view because I have moved to my left. So if I move to my left, then the wall to the right will be the right profile plane where I will be getting the left hand profile view or left hand side view. So in that case, the projectors again, by the rule of orthographic projections, the projectors must be perpendicular to the plane on which we are taking the image. So that means the projector will be in one direction, there will be only one projector. So wherever it meets, this projector, wherever it meets the profile plane, here I will get the left profile view or the left hand side view as P double dash, and we denote it by smaller case with 2 double dash. This is the notation, or this is how we denote the profile view. So if it is P dash, that means it is front view. If it is simply the smaller case P, it is the top view. And if it is P double dash or the alphabet with a double dash, it will be the side view. Now when we move to the side, we will be able to see the height as well as the distance of the point from the vertical plane. So this same distance is going to, so this is perpendicular to this, and the height will be perpendicular to. So I will be able to see the height HMM as well as the same B millimeter distance both together in the profile view, and thus I will be getting the left hand profile view. Now again, as we have turned the horizontal plane to make these two planes coplanar, similarly I will have to rotate the profile plane also to bring it to the same plane so that I can draw the image, because we are drawing on a sheet or a paper, and paper is a two-dimensional object. So if I rotate it this way, then these two images will superimpose, the front view and the side view. So we will not rotate it this way, rather we will rotate it to the other side. So we rotate this as if we open this room or this box, so it gets turned and the side view also gets rotated with the plane. So we get the profile view here. So when we are rotating, you can see, so when I am rotating this and opening it, the height of this image is not going to change. So it is the same height h which is getting transferred, right? And this is the b distance which is getting turned. So that is how. So this is the distance from the vertical plane, and we have seen that there will be another intersection line. So this is another intersection line. We name it as x1 y1. So this x1 y1 also becomes a new reference line. So that is how I'll begin. So I get the front view above the xy line, the top view in front of the xy line, and the side view or the left hand side view to the right of the front view. Fine. So now if we go for the orthographic projection of this point and try to get all the three views, let us see, without drawing the pictorial understanding, just imagining the condition how it can be. So there is a point P in the first quadrant, so my drawing will start with a reference line. So I draw this reference line as xy. Now how many points? There is only 1 point, so for 1 point there will be one projector. So I draw the projector for that line, and projector will be always perpendicular to the reference line xy. So if I know the height, so at h height from the reference line, I can mark the front view image of this point. So this is P dash. At b millimeter in front of the xy line, so let us say this is point, top view of the point P. So I have the front view and the top view with me. So I have H and B with me. So with the help of the front view and top view, now I'll go for the left hand side view. So left means from this position, as if to my left, I am standing here and looking at the point in this direction. So when I am looking at the point from this direction, that means I'll get the, so if I am moving to left, I'll get the left hand view, left hand side view to the right of the front view. So from here at a comfortable distance, I can draw the other reference line, so which is x1, y1. So this will be the area for the left hand side view. So we have seen in left hand side view the height as well as, so if this is the point and if I am moving to the left and looking at it, I am able to see its height as well as how far it is from VP. So both H and B are visible to me. Now when I am opening this, the height is not going to change. So I can simply drag this dimension to this area. So I can draw one line parallel to the reference line from the height of this point. So I'll call this as locus of point P. So it is the same height. So that means the side view image is going to lie on this line somewhere. Right? And where? So this is the B millimeter. So I'll bring it here till this point, till x1, y1. And from here, as if this becomes the origin. See, when we have opened it, the B distance is also getting rotated, right? So B distance from the origin, it will get rotated, which is having this radius as B millimeters, and then we project it. So the side view is going to lie on this projector, the side view is going to lie on this locus. So that means the intersection of these two lines is satisfying both the conditions for the left profile view. So wherever these two points, these two lines intersect, this intersection point will be the left hand side view of the point P. So this is how we get the image of a point which is in the first quadrant and h mm above HP and B millimeter in front of VP. So now we will move on to the next case. So this is the second case where point Q is on VP and it is h mm above HP. So now when we are looking at it from the front, we will be able to see the front view image of this point where the point is. So as if Q, if you want to imagine, there is a switch on a wall. So where you will get its image? There itself. So I am getting the front view image of this point Q there itself. For the top view, when I am looking at it from the top, you will see that, so when we pass the projector through the point Q, so we get the top view image of this point Q on the reference line as Q. As far as the profile view is concerned, so I'll get the profile view on the profile plane. So this is the profile plane. So if I move to my left and look at the object, so the projector, I'll be able to see the side view image of the point Q as Q double dash on the x1 y1 only. So its representation in orthographic projections will be, so there is one point, one projector. The projector will be perpendicular to the reference line xy. Now in the front view, I'll be able to see this height h mm. So I can mark that h mm. So I get this as the front view image Q dash. Now it is a zero distance from VP because it is on VP itself. So that is why I'll be able to see its image on the intersection here. So at the intersection, that means on XY line, I'll be able to see the top view image of this line as Q. What about the left hand side view? So left hand side view will be always to the right when it is first angle left hand side view. So this is the front view, this is the top view, and the left hand side view I'll be projecting the height. The width B is 0, I rotate it and project. So here itself I'll get the the side view image or the left hand side view image here itself. So this is the second case. Similarly, the third case, if we see, so for third case, let us say there is a point R. Now it is on HP, as if there is a coin which is on the floor, right? And it is B millimeter in front of VP. So it is B millimeter in front of VP. So let us say the point is lying somewhere here, which is on the floor or the horizontal plane R. So when I am looking at it from the front, the projector will pass through R, and wherever the XY line, so I will be able to see the front view image of R on the XY line as R dash. For the top view, when I look at it from the top, I will be getting the top view of point R there itself, right? And what about the side view or the left hand side view? So when I move to my left and look at it, so I will be able to see the side view image as here R double dash. So how are you going to represent it in orthographic drawing? So this is the reference line XY. For one point, there is one projector. So this is the projector of R. The height is 0. So the height is marked. Height will be able to see in the front view. So this will be R dash as the front view, we'll get the front view on the XY line, and B millimeter in front. So B millimeter in the horizontal plane. So when we are rotating this B millimeter, so B millimeter in front. So this I get as the top view image R of the point. What about the left hand side view? Left hand side view will be to the right. So at a comfortable distance, again I'll be drawing the other reference line x1, y1, which will be again definitely perpendicular to the xy. So x1, y1 is perpendicular to xy. So height is 0, so locus of R will be the same, but the B distance will come till the x1, y1, and from the origin it is going to turn. So I get the side view image R double dash as this. So this is the third case. What can be a fourth case? When a point is on the both the reference plane. And what is that location? Very correct. The XY line. The XY line is on the horizontal plane as well as it is on the vertical plane. So let us say if there is a point which is on the XY line. So if it is on the XY line, when I look at it from the front, I'll get the point where it is. So the front view image S dash will be there itself, and the top view image also, if I look at it from the top, it will be there itself. So from the side view, if I see, I'll be able to see the S double dash or the left hand side view on the intersection of the XY and the X1, Y1. So how I can represent? So this is the reference line XY. Projector for S, 1 point, 1 projector. Height is 0 as well as distance from VP is 0. So we'll be able to see the front view image here itself on the XY line as well as the top view image here itself on the XY line. What about the left hand side view? So X1 and Y1. So project height, width, rotate. So I'll be getting the side view image as well on the XY line, but at the intersection of X1, Y1 and the XY line. So thus we have seen all these conditions for projection of points. So let me just revise what we have seen. So say this is the reference line XY. Now here I am not going to again express the side view. Our first case was point P, H millimeter above HP, B millimeter in front of VP. So for case 1, so this is the projector of point P. So this is the front view P dash and this is the top view P. For second case, what we have seen, the point is in VP and H millimeter above HP. So projector of point Q, it is in VP. So and H millimeter above HP, that means in front view I will be able to see. So this is Q dash, and B millimeter, now here it is on VP. So the distance of this point from VP was 0. So I get the top view at the XY line. So this is the top view. In the third case, we have seen that the point is on the horizontal plane. That means the height is 0 and it is B millimeter in front of VP. So it was the third case. So 1 point, 1 projector, and keep in mind projectors will be perpendicular to the XY line. So in this case, point R is on the horizontal plane. So height is 0. So height is 0. So R dash, and it is B millimeter in front. So this is the top view R. And in the fourth case, we have seen that the point is on both the reference planes. So if a point is in both the reference planes, that means it is on the XY line. So height is 0, the width is also 0. So 1 point, 1 projector. So I get the front view also on the XY line, that is S dash, as well as the top view there itself as the. So these are the basics of projecting a point. So when we understand how to get the image of a point, then if I can get the image of a single point, I can get the image of various points. So there we can extend our idea to get the projection of lines, planes, then solids likewise. So that is all for this session.